Problem number 31. A rectangular... Folks, I'm so tired. I'm doing my best here. I'm sorry I'm not more enthusiastic in these videos. A rectangle is inscribed under the graph of y equals 2 times the square root of 5 minus x. Let's picture this situation. 5 minus x means 1, 2, 3, 4, 5. So this graph is going to start there and move over like that. What's going to be the value of that y-intercept? I don't know, 2 times the square root of 5, which is probably, I don't know, around 5 or so. It doesn't matter, because what does matter is the situation. And the situation is this. I have a rectangle that looks like that. There's the top, there's the side, the bottom is on the x-axis, right there, my very crooked x-axis, and then there's the other side. So let's think about dimensions here. If I label this point, the corner of that rectangle, as x, comma, y, it tells me that the base of this rectangle is x, and the height of this rectangle is y. So the area of this rectangle is x times y. And I can't do anything with that. I want to maximize the area of this rectangle, and to do so, I need to write the equation of the area of this rectangle, which I've done, but it's not a great equation because it has 3 variables, and we would like our equation to have 2 variables, an independent variable and a dependent variable. So what I need to do is I need to rewrite this as a equals x, but instead of y, I'm going to write my equation, which is 2 times the square root of 5 minus x, because that's just a better way of writing y. So that's going to be my area equation. I should then graph this on my calculator, so enter that into y1. So you'll have to remind yourself that your y values are really areas. So y1 equals that. Go to your window, x min 0, x max 5. And then at this point, I would hit zoom fit by choosing smart x values. You can then do a zoom fit, and you'll get a perfect window if you choose the x-intercepts as your, or if you choose the domain restrictions as your x-min and x-max. So when you graph that, you'll get like a pretty cool looking graph that looks kind of like half of a guitar pick. It looks something like that. Kind of like a parabola that's leaning to the right a little bit, and we want to calculate that maximum value. So second trace gets you to calculate option 4 for maximum. Left bound, go to the left. Right bound, go to the right of that maximum. We know that 5 is to the right of it, so I'm just going to type 5, guess, going to hit enter, and it's going to tell me that this maximum right here occurs when x is 3.333. It's probably 3 and a third, because calculator rounding, it's probably exactly 3 and a third, but who knows, let's just call it 3.33. And then it says y equals, which is really area, equals 8.6066, so 607. And we want the dimensions of the rectangle as well as the area. So we have the x dimension, we have the area. We now need the height of the rectangle. And the height of the rectangle is the y value of our original square root graph. So we need to take this 3.333 and we need to evaluate the original y function at 3.333. So 2 times the square root of 5 minus 3.333. And we get that y, the height of the rectangle, is 2.582.